Alright, today we're going to be doing a coordinate transformation, and we're going to be going from a Cartesian to a polar coordinate system. Now, usually when these things are introduced, they're introduced to solve a rotational problem of some sort, but don't be confused. So this right here represents the point particle, okay? And this right here does not represent an actual constraint. It will eventually be included in some of the problems, but this is the same thing as this. So this right here is simply the position. And to describe this position, we use the vector r vector, so we call it, but it's the magnitude times the r hat. It's just the magnitude of the distance from the origin to that point. But the main thing to know is that's really just what it is. It's just a position vector, and it has nothing to do, this right here is not an actual physical thing or like that. So, because that can cause some confusion or make you think in a limited way. Okay. So to start off, it is mathematically okay to take a derivative of this, and we're going to do so by using the product rule. Okay, so we're going to write it out like we have here. That's the r vector times the magnitude times r hat. And we're simply just going to take the product rule of this. And I use brackets to when I write the derivative, and then parentheses for the one that I'm keeping the same. So we got r dot, and then the r vector stays the same, and then so yeah, these, by the way, are not vectors. This is the magnitude r dot, the change in the magnitude. Okay, so that's r dot, r hat, and then the magnitude r times the derivative of r hat respect to dt. Now the thing is, we're going to have this and one more, which is complicated at first because these are not like x, y, and z hat. R hat is a unit vector, but it changes with the angle. So I'm going to show you how to go about fixing that. Okay. So again, here's your r vector, and here's your r hat, and what we have also is a theta hat. Now the reason for this is we need to have an orthogonal system. If we have two unit vectors that are orthogonal, then we can describe the entire system. So that's why we do that. We got to have the r hat, and then to make convenient, we introduce what's called theta hat, and that is simply perpendicular to r hat. Okay, and if you can imagine, without going too far into it, without going over on time, you can imagine drawing this as a r vector 1, and imagine some angle later, r vector 2. It's hard to imagine now that I write it, but you can imagine that there'd be that change between those, and as long as that theta is small, that would be almost perpendicular, and that's what we get, is the limit of d theta goes to 0. Okay, so to mathematically solve these, we're going to have to actually define r hat and theta hat in terms of stuff that is easy to take the derivative of. So I'm going to follow it through. Unit vectors have a value of 1. So in using vector addition, if a vector was to point this direction and up, the combination would equal r hat. And then we have r times the sine, r times sine of theta y hat, and then for the x would be cosine. Now for this one, it's a little tricky, but not too much, because this one's going to the left. If we just break this up into x and the y, this would have a negative direction, but still. So this, and again, this is theta, and this whole thing is 180. Straight line's 180, theta plus phi plus 90. So we know theta plus phi is 90. Then you could use some algebra to figure that this is theta. This is not theta, this is. And then so to get the x values, we would use 1, because the magnitude of theta hat is 1. So that's 1 sine, or negative 1 sine of theta to get that x hat. And then positive cosine y hat to get the y direction. And from there, we can just simply take derivatives, nothing too complicated. And I'm trying to keep this quick, so I'll make a more in-depth video, but this is trying to keep it quick. So y'all just pause it and go through that, okay? And then if we factor out this theta dot, we're left with this expression, which if you look over here, is equal to theta hat. Negative sine theta x hat, cosine y hat. There it is. And then so we'll have this is equal to theta dot times theta hat. Same process, again, not too complicated, follow it through, and you could factor out negative theta dot, and then this expression here is r hat. And again, pause it to work through that. Okay, so this is the velocity vector of a particle. And again, going back to the first page, this is not necessarily constrained to a circular path. This could be free fall, or this could be a one-dimensional problem. It would be convenient, but for the sake of argument, just so you understand the concept, it's simply a coordinate transformation. This is not limited to a pendulum type motion or anything. This could be any type of two-dimensional position problem. And so now we have the velocity of it, and we have the different components in the r hat, and then once we expand this out, we'll figure out that there's some theta hat components in here. So that's the one we did earlier. You fill in theta dot theta hat, and you get this expression right here. So now this is again orthogonal. Some of the components of velocity are r hat, some are in the theta hat. And just with those two, using vector addition, those two vectors, r hat and theta hat vectors, can get the total resultant vector to describe a velocity. Okay. And again, this is where I take the derivative of velocity again to figure out the acceleration. Nothing new. You're going to have some derivative r hat with respect to time and also theta hat, but we've already solved those. And we're just going to go ahead and work it through real quick and expand it out. Here is the first term. The product rule for this one. Now this one's a little tricky because we're taking the derivative with three terms. But an easy way to go about that is just to take r theta hat. To take r theta dot, those first two terms, and make them one term. So anyway, the first term is the product rule. The second term, which is really the first two terms with the derivative of the first two terms, multiplied by the second term, theta hat. And then we keep the first term, which, like I said, is those first two terms, and then multiply by the derivative of theta hat. Again, we know theta hat to be negative theta dot theta hat. Okay. And I put stars. These are the ones that were the tricky ones. And I put stars here when I have expanded them out. Okay. And again, I'll make another video a lot more in depth with a better viewing screen, but okay. and then you combine like terms, expand everything out, and you get it into this nice formula right here, or equation. That is the second derivative of the change in magnitude, not the vector, but that's the second derivative, the change in magnitude from the origin. That is the R constant, and all these go through. And then in a later video we'll show in a real life application which terms are important to us when we're solving a problem.